Hello, good morning, everyone. My name is Shamriddhi Shankar Rai. I'm a faculty member here. So I would like to welcome all of you to ICTS TIFR. Unfortunately, our director, Rajesh Gopakumar, he's traveling. Otherwise, he would have welcomed you. So I will sort of just introduce ICTS to many of you who've sort of been here, know the place, but we always hope that we have newer friends who are joining us for the first time. So this is where we are. This is what the campus looked like a few years ago, and now it's much more green. There are sort of more people, more trees, more greenery, and this is again a nice sketch presented to us by one of our visitors in a program like you are in a few years ago, and this is basically overlooking the library. You'll see in ICTS there are lots of blackboards around. This is a mathematics program, so I'm sure that all of you will appreciate all the blackboards, and I'm sure that you will make very nice use of it. Often we have not just mathematics, but very nice sketches made by students and visitors, so that's an example of that. So coming to ICTS, ICTS is amongst the newest centers of TIFR. Many of the organizers in this program are from one of our sister sort of units, TIFR-CAM. And ICTS really has a three-pronged mandate, which is programs, the sort that you're in, which go on for often 2 weeks, 3 weeks. This is a 2-week program, essentially. And sort of it aligns closely with our other mandates of in-house research and outreach activities that we take seriously. And so this is sort of the center is built or patterned on several other centers across the world, KITP, MSRI, IIS Princeton, but with its own sort of unique flavor that we hope we bring to it. So this is a snapshot of our faculty members. We are growing. A few years ago, you would have seen fewer pictures, but it's a young campus, it's a young center, but which is growing rapidly. So just to sort of highlight some of the in-house research that happens here. So we have a sort of loosely a PhD program, lots of postdocs and faculty members. We don't have departments as such. This is sort of loosely structured, so different people with different persuasions are always speaking to each other. But broadly, we have people in the areas of dynamical systems, PDEs. This workshop, this program is really sort of targeted at PDEs. Then there is a group which works on algebra, geometry, and mathematical physics. Then there are whole sort of probabilists. We have 3 of them right now. Theoretical computer science, quantum computation, astrophysical relativity, and astrophysical fluids. Then there's a sort of big group working on essentially the physics of complex systems, defined roughly in the areas of condensed matter, statistical mechanics, and fluid dynamics, as well as a quantitative biology group, which is sort of happily growing at pace. And of course, there is a string theory and quantum field theory group, which sort of looks at problems in string theory, quantum field theory. We have several sort of international partnerships. So some of them are listed here. There is an IRP with CNRS in France. We have 5 Max Planck partner groups, which are doing wonderful work. Then there is, of course, an Indo-US Center on Extreme Gravity. We also sort of host these exchange programs, or as well as schools in partnership with similar centers elsewhere. For example, we have this wonderful sort of successful winter school on quantitative biology, which was running for over a decade with the ICTP in Trieste. So the ICTS programs, and all of you are part of it now, in some sense, sort of covers a big span of several different areas in largely in the natural sciences. So yeah, if you go around and look up our website, you will find many of those. And this is for people who might want to organize a program like Professor Sandeep this time. And so this is how we do it. So there's a twice-a-year call for proposals, which are vetted by your program committee, and we provide all sorts of support. Typically, we have a packed schedule. There is hardly a sort of a couple of days that go by when there are no programs at the institute, at the center. And this sort of allows us to be a sort of science hub for the country with several research publications which come out of such programs, often because it allows people to nucleate and talk with each other. All our talks are basically archived on this sort of ICTS talks on YouTube. And you would find, if you go there, I'm sure you'll find enough talks which are of interest and relevant to your own scientific interests. And sort of this has also allowed us to sort of provide roadmaps by sort of encouraging new directions, which are often nucleated through such programs. And here you have a sort of list of very different sort of areas where we hope to have excited a new sort of direction, a new sort of research, especially within the Indian context. We already discussed a bit about these advanced level training schools that we host, which is really for hands-on training for young people who are starting to work on some of these areas. Apart from that, we have these special lectures. There are 8 of them in different areas of sciences, including things which touch upon, for example, the Conformally lectures, which touch upon things which are, not always in the ambit of pure sciences. As I mentioned, one of the mandates of ICTS, apart from programs and in-house research, is our outreach program. And this, again, is a sample of the sort of different outreach lectures that we provide for the sort of larger community, for society, which sometimes they happen not here, but in the city, in the planetarium and elsewhere, which is open for the general public and targeted for people who are curious. And part of that also is to engage in schools to sort of work seriously on science pedagogy, science communication. We have several, especially a lot of them are for mathematics, essentially. And there are a lot of these things, especially the math circles. So often on a Saturday, you'll find lots of young students from neighboring schools elsewhere doing hands-on sort of mathematics, if you like. And that's something which I think is fantastic to be involved in and part of. So with that, I thank you for your attention, and I wish 2 weeks of very productive and very engaging and very fruitful program learning and fun. So thank you very much, and I wish all the best to all of you and the organizers. Thank you.
Okay, so let's begin our program. And we have the first series of lectures by Professor Yannick. First of all, let me like to thank him for agreeing to give this series of lectures. So he was supposed to be here with us today, but unfortunately, due to various issues related to visa, he could not be here. And it was very kind and generous of him to agree to give these talks online, even though the timing is not very convenient for him. He's in US. Okay? So for that, first of all, let me thank him for agreeing to give this talk with all these troubles. Okay, so Professor Yannick doesn't need any introduction to most of the people here. So however, let me just give a brief introduction. He's a distinguished professor of mathematics at Rutgers University, and he's also a director for the Center for Nonlinear Analysis. So he did his PhD from Courant Institute, and after that he has held various positions across various prestigious institutions. And his research interests are basically in conformal geometry, partial differential equations, and various problems related to that. Okay. So he has been awarded various recognitions for his outstanding research contributions. He was an invited speaker of the International Congress of Mathematicians in Beijing in 2002. So he is a fellow of the American Mathematical Society and a Simons Fellow. These are only a few things to mention. So without any further delay, let me request Professor Yannick to begin his lectures. And he is going to speak on conformally invariant elliptic equations of second order. Over to you, Professor Yannick.
Thank you. Thank you very much. Thank you for the kind introduction. It's a pity that I'm not able to come here in person. So it's a pleasure to give it online also. Okay, so I think the lectures will be somewhat informal. Okay, so what I describe will be about conformally invariant elliptic equations of second order. And so this is something, an area I have been working. Yes. So so this is conformally invariant equations. For me, these studies are very much related to my study on the Yamabe equation. So I will start with that and then go to the kind of fully nonlinear part. So I will first describe about Yamabe problem. So we look at a closed Riemannian manifold, compact. So the question is whether there exists a positive function such that the conformal metric satisfies, so the so-called scalar curvature is equal to constant. So in two dimension, if you state it as two-dimension Riemannian manifold compact, whether there exists a conformal metric so that the Gauss curvature is constant. So this is always yes. This is called uniformization theorem. Very classical. Go back to Poincaré and so on. So for the Yamabe problem, so the existence is known. So the year is easy to remember. If you remember the first one, add 8 to each, you get the next year. So this question is actually equivalent to, so this is equivalent to, for the solvability, solving the following elliptic PDE of critical exponent. So the equation is So the result is you can always solve it with some constant. So actually, to solve it, this constant has to be of the same sign. So this operator, this is a second order linear elliptic operator. You denote it by LGU, the conformal Laplacian. So it is elementary to see that for this equation to have a solution, this C has to be of the same sign of the first eigenvalue. If lambda 1 is positive, then you have to solve for C is positive. So this work says you have solvability. Yeah, you can solve it. So after knowing the existence of this, so there are work on a solution space. So you would like to know on a manifold, because we have solution, you want to know about all the solutions to the problem. So if you look at the negative case, so negative case meaning that this lambda 1 first eigenvalue is negative. So this is negative, so you call it negative case. So the fact is solution is unique. This is quite a elementary fact. It's a very good exercise to students. Another case is the arrow case. Namely, this lambda 1 is 0. This is 0. So then the equation you solve is actually a linear equation, because this will be 0. So the first eigenvalue is 0. So the solution space is known that it's one dimension. This is a first eigen space. So if we look at positive solutions, so all the solutions are given. So all the solutions will be given by phi is positive, phi is eigenfunction. So this is one dimension. So this is one dimension. Or you can say this is A phi. So phi is one positive solution of LG phi equal to 0, A positive. So you just take 1, you multiply that by positive number. So that's all the solutions. So it turns out that the positive case is very delicate. So first, it is known that Sn has many solutions, and it is actually classified by Obata. And so all solutions are non-compact. So because the conformal diffeomorphism group of the standard Sn is non-compact. Actually, that's the only compact Riemannian manifold. Its conformal diffeomorphism group is non-compact. So if the manifold is locally conformally flat, but not diffeomorphic, conformally diffeomorphic to Sn. And in that case, this was proved by Shane. So this is actually compact. So this case is compact. Meaning, when I say compact, I mean that all the solutions of this equation, positive case, you put C as 1. You look at all solutions. All the solutions will be first bounded. Once it's bounded, you know that both U and U inverse has all the derivatives to be bounded. So that means compact in very strong norm. So when it's not locally conformally flat, so it turns out to be very subtle, very delicate situation. So for n, so this case is more subtle. So for this is in 3 dimension, it is compact. In 4 dimension, it's also compact. And then there are independent works all the way to here, and then up to 11. Then there's this spectacular results. So it turns out for n less or equal than 25, it is compact. And for n greater or equal than 25, it is not compact. And more recently, it is proved that not only it blows up, there's a sequence, it blows up in L infinity norm, it actually blows up in volume. So L2n over n minus 2 norm. It is still desirable to know more about this compactness and non-compactness to have more understanding what kind of geometric conditions guarantees compactness. For example, if you know the sequence of conformal matrix have a Ricci lower bound, it is known to be compact. So for all the compactness results, above, So for all the above mentioned compactness results, so the Liouville type theorem of Cavalli-Gitta-Sprague has played a crucial role. So this Liouville theorem says that if you have a positive solution in Rn, then they have to be of this form. So in this case, the conformal metric is actually the sphere, yeah, like a constant curvature 1, scalar curvature 1. So of course, improving the compactness result, this Liouville theorem also plays a role. Used also, but this is very standard. And there have been, for many years, there have been study of the so-called fully nonlinear Yamabe problem. So what it's about is like this. You take a compact Riemannian manifold of dimension n greater or equal than 3, and this is the AG is equal to that. This is the Schouten tensor. And you let lambda denote the Schouten tensor, eigenvalue of the Schouten tensor with respect to the matrix G. So you look at this problem. So you take a function of eigenvalues of the Schouten tensor. You want to find, so the problem is initially you assume the Schouten tensor have eigenvalues in gamma. The question is whether or not you can find a conformal metric so that f of that is equal to 1. So you can say the f curvature is 1. So if we take f to be equal to the sum and gamma equal to this is the Yamabe problem in the positive case. This is a positive Yamabe problem. It's exactly. So one can say that we are looking at this problem for more general f. And consider, so what is gamma? So in this first lecture, this will be our gamma, at least. So the gamma is a open and symmetric cone vertex at origin. Gamma plus gamma n is gamma. So let me draw a picture in R2. So in R2, I draw, this is lambda 1 and lambda 2. So gamma 2 is the first quadrant. So this means those lambda, both lambda 1 and lambda 2 are positive. So gamma, I can draw a gamma like this. I can draw a gamma like this. This is a symmetric, meaning if lambda is in it, you permute the lambda i's, it's still in it. So this is a cone vertex as origin. So this condition meaning that at every point here, you take any point in your gamma, you move the first quadrant there, this part should be in gamma. So then it satisfies this condition. That's exactly what this condition is. So the cone can be like this also. So the largest is to be here. If you keep opening up, going beyond that, it's not going to satisfy this condition. So these are some often used, rather typical gamma k. This is case elementary symmetric function, and so on. So so here is a problem which has been studied for a long time. It's still quite, there are some remaining open problems here. So does there exist a conformal metric? So this is the question. So as I said, if gamma equal to gamma 1, that's the Yamabe problem. We are talking about Yamabe problem. So this is a fully nonlinear version of that. So there are results. Mainly, one can say here are the, so first, we know that when F gamma is sigma 2 and gamma 2. So these are the Chan-Gursky-Yang first proved that for dimension n equal to 4, for sigma 2, it is solvable, and solutions are compact. So this is for higher dimension. And for locally conformally flat, for general F, this is always true. If gamma belongs to gamma n over 2, so this is for sigma k bigger than n over 2, this is for borderline sigma k equal to n over 2. Yeah. Oh, and also for this. So for instance, open existence, let's say for sigma k gamma k bigger than 3, less than n over 2. So this is open. Compactness, for example, in the sigma k gamma k case, 2 is also not known. If you know compactness, you will be able to prove existence. Okay. So to understand such fully nonlinear Yamabe problem, a central issue in the study is to establish associated Liouville type theorems. So today I will mainly talk about Liouville type theorem. So why it is relevant, this Liouville theorem? So for one thing, if we want to prove compactness, so you want to prove all solutions are bounded from above. By now, if you proved upper bound, you will be having lower bound and all derivative bound. So this has been developed in the past 25 years, 20 years or so. So one wants to know whether you have upper bound or residual upper bound. So if we want to prove it by contradiction argument, then we can say, suppose not, then there is a sequence such that this sequence, the maximum goes to infinity. So here, then you make suitable rescaling, then it will lead to an entire solution of the corresponding equation in Rn. So here is an equation. Is the equation you get. If you normalize it suitably, you will get this. So this f will be a symmetric function, and now you get an Rm. So this AU is a little bit long, but it is actually canonical. It is conformally invariant. This is which I will explain what that means. So you will see that this is a canonical one. So here we call this AU conformal hashing. So I write it shorter because this will be longer. So I write it, for example, in terms of W. Then it becomes shorter. So it has the Hessian. This is a gradient, and this is n by n. I is n by n identity matrix. Okay. So we are talking about functions. U is a function on Rn, function, positive function on Rn. So let phi to be Mobius transformation. So namely, it's generated by X translation, or X go to AX, A positive, or X goes to X divided by X squared, and finite composition. So finite compositions of that, we call it phi Mobius transformation. Whenever you have a function u and you have a phi, so you have a u phi. So this Mobius transformation form a group. So you have group act on these functions, u phi. This is the composition. J phi is the Jacobian of phi. So this is the determinant Jacobian. So here is the property of this AU. It is invariant. So AU phi, the eigenvalue, and AU eigenvalue, they differ by orthogonal conjugation. So therefore, they have the same eigenvalues. So, so in particular, you can see that if f of AU, I didn't write the lambda, so yeah. So if f of lambda AU is 1, clearly you will see f of lambda A u phi will also be 1 because of this. So whenever you have one entire solution here, all the group u phi will still be solutions. So, and also, this AU has the following property. Whenever you have a second order operator, it is group invariant. It is invariant, Mobius invariant. Then it has to be of this form for this AU. Yeah. So in that sense, this AU is a canonical object associated with conformally invariant equations. So as I said today, I mainly only focus on the Liouville theorem. So this is a Liouville theorem jointly with Baozhi Zhu and Zongyuan Li. So the assumption is we have a gamma satisfying these two conditions. Okay. So these are the conditions on gamma. So you can easily draw such gamma in 2 dimensions I described. So in 2 dimensions, the gamma will be, this is the smallest. You open it up like this. You can open it up more, and the large, then the most you can do is this one. Okay. So if you go like this, so this fails. If you, I'm only looking at this side. This fails this one. So this condition will no longer be true. Because if I put the point here, gamma, I translate my gamma n, it goes out. So this is bad. Okay. So, so these are the two conditions. So now I assume further we assume further that there's a special point here. Okay. I assume it's not on the boundary of gamma. So if I write in R2, this gamma, this point is exactly on here. So if I call gamma 1 to be the lambda 1 plus lambda 2 be positive 0, so this will be boundary gamma 1, and the point lambda star will be exactly here. So this is the picture in R2. Will be exactly here. So if I draw a picture in R3, so I can, it's not so easy to draw. So I will pretending this is R3. So then this surface is lambda 1 Rn, for example, n greater or equal to 3. So lambda n positive. So here, lambda star will actually be outside gamma 1. So gamma 1 will be, this is gamma 1. So in this case, lambda star is here. So lambda star is not in gamma 1. So in this case, lambda star is in Rn minus gamma 1 bar. Yeah, gamma 1 bar. So, or, yeah, lambda star is here. So that's the main, because when you sum it up, you will see more negative. So the theorem is you assume this lambda star is not on the boundary of gamma. You assume that. So that's the condition. You have a cone, this point should not be on the boundary of gamma. Then, if you take u to be positive and satisfy this equation. So this is a equation. Actually, it's a degenerate elliptic equation. So lambda of AU belongs to the boundary of gamma. Then U must be constant. So that's the Liouville theorem. First, if gamma equal to gamma 1, so this is the Liouville theorem. So lambda star AU belongs to boundary gamma if and only if Laplacian U is equal to 0. So this is Liouville theorem. So that gives you the Liouville theorem. So this is a nonlinear extension of the Liouville theorem. So this condition is optimal in the sense that if lambda star belongs to boundary gamma, it fails because if log u is linear function, it's always a solution. It's always a solution. So here we again mention some examples of gamma. So these are standard examples. This is a kth elementary symmetric function. This gamma k is the point where lambda 1 up to lambda k, they are positive. And it is the component, this is equal to the component of those lambda which make them positive containing the positive cone. So they are the same. They are the same. The equation, this equation is actually a degenerate elliptic equation. So to prove this theorem has some difficulty coming from the degeneracy. If we take k equal to 1, that's harmonic function. There's no degeneracy. And these examples are given before. So this equation, Hopf-Lehmann fails, strong maximum principle fails. So previously known Liouville type theorem. So first, if in R4 gamma 2, so this was proved by Chang, Gursky, Yang. And if gamma belongs to gamma 1, so it was known before, if gamma belongs to gamma 1. So the main thing, the new thing is to go in beyond gamma belongs to gamma 1. And second is to identify the optimal condition in the sense that, more general, yeah. And the reason, the main difficulty here is to treat isolated singularity of this equation. So that's the main thing, is to understand isolated singularity to such equations, like removable singularity, removability of singularity, and so on, yeah, point singularity. Okay, so I remember that many years ago, when I gave a talk on this, Peter Lax told me that he had previously considered the question of determining for which set, if the eigenvalues belongs there, if he didn't say eigenvalue, he's, if the Hessian belongs to the set, okay, forces you to be a constant. He actually thought about extending Liouville theorem that way. So here are some examples by selecting appropriate gamma. So if we order eigenvalues lambda as this, so here is a statement. So for I not equal to 1, if lambda I of the Ricci of the conformal metric is 0, then this U must be constant. So therefore, G tilde is the Euclidean metric. And this statement fails if I is equal to 1. There's also another Liouville type theorem. So this gamma is the same. So now the lambda star does not belong to gamma bar. So what that means is, so if your gamma, for example, if your lambda star is here, lambda star is here. So you know this is the first quadrant. This is the first quadrant. You start to opening up, for example. So as long as you do not include this point, so the theorem holds. So here we know that this lambda AU belongs to gamma. So therefore, we have certain positivity for your matrix AU. So here, if you open too much, you go over the borderline of this positivity, this Liouville theorem actually fails. So the theorem is like this. So if you have a solution of this, then this must be U must be that. Then if lambda star belongs to that, meaning you opening up this going too much, you lose positivity you need. So you go this lambda star here is the borderline for the positivity. So then there's a counterexample, smooth F, smooth U, so that U is not of the form. If you take here, if you take F gamma equal to sigma 1 gamma 1, then this is the theorem of Caffarelli-Gidassen-Sprague. Because if you take the trace of this, if you are lambda I AU, you take sigma I equal to 1 to n. This is sigma 1, this function. If you take F equal to sigma 1 in gamma 1, this is identically equal to minus Laplacian U divided by U to the n plus 2 over n minus 2. This is an identity. So if you set it equal to 1, that's exactly the Liouville theorem. Okay. So if F gamma is sigma 2 gamma 2 in R4, this was first proved by Chang-Gursky and Yang. And then Albin Lee and I extended to sigma k and so on, and also extended to gamma belongs to gamma 1. So, so the proof follows this by moving sphere, and the only thing we need to treat is an isolated singularity, because in here and in all other proof for such Liouville theorem, we always used that Laplacian U is less or equal than 0, one way or another. So this has been used, built in into the proof, because lambda of AU belongs to gamma 1 will give you this. This is if and only if. You will have Laplacian negative. So now, in our case, gamma is not there. So we need to handle a solution which is in a punctured ball. So we need to understand this solution behavior near 0. So the needed behavior holds if this condition holds. And if this condition fails, the needed behavior fails. Not only that, so the theorem actually doesn't hold. So in a way, for the above two Liouville type theorems, the conditions we give for the positive result are actually necessarily insufficient. So here are examples. So if you look at a conformal metric in Rn, and with this order, if the lambda i's Ricci is 1, then it's conformal to a sphere. If I equal to 1, this is not true. Yeah. So let me describe the, yeah, maybe I go this way is better. Okay. So I want to describe the proof of theorem 1. So theorem 1 is about the extension of the classical Liouville theorem. So it reads like this. So we have this condition of gamma, and this point is not on the boundary if eigenvalues of this conformal Hessian is on the boundary of this cone, then U is constant. So we give a proof for this case, okay? Because there are the other case proofs are different actually. So this is one case. So we use a new proof of the classical Liouville theorem somehow. It's a different proof from textbook. Okay. So how to prove this? So for every x in the space and for every radius, so sorry, I used the lambda as a radius now, okay? I should use another letter, but I'm so used to this, use lambda. So this is the Kelvin transformation. It turns outside the ball to inside, inside to outside, and keep the boundary not moving. So the point is we are going to use this property. This is conformal invariance. So if Laplacian U is 0, then the Kelvin transformation is also harmonic. So you know that this is harmonic in a punctured ball, and U is positive also. Then we know that the point singularity can be removed. It's still a super solution. So this is a classical result, and to remove a singular set, in this case, a necessary and sufficient condition is the Newtonian capacity is 0. In this case, certainly it is. So now we are in a situation that we are in a punctured ball. In a punctured ball, you have superharmonic. So now, not punctured, but in the full ball now. So you have superharmonic, you have harmonic, and boundary equal. And that, by the comparison theorem for Laplacian, we have this. So any function with this property will be a constant. So that has nothing to do with PDE. So any function with this property. So the function has the property that take any ball in the space, the Kelvin transformation is greater or equal than U inside. So U is constant. So if you look at this proof has an advantage. This proof uses conformal invariance. So uses this. But the equation we are looking at is conformally invariant. Lambda of AU belongs to boundary gamma, is conformally invariant. So therefore, we are in a situation that so originally you have a solution in the ball. in a ball. In a ball. And you have another solution, which is a Kelvin transformation. It's in the ball, in a punctured ball. In a punctured ball. And u phi is equal to u on the boundary. So now, if we are able to prove one, your solution is actually a solution in the ball. So namely, if you can extend, you can remove the point singularity, that you cannot, actually, you can make it super solution. You are not able to make it a solution. You can only make it a super solution. So if you can do the following, you are in good shape. So you want to have lambda AU phi is a super solution in the ball. Okay, you want that. So second, you are able to do comparison theorem. Namely, if I have a solution, super solution in the ball, you have a solution in the ball, and they agree on the boundary, then the super solution will be greater or equal than the solution. So if you are able to establish these two, then you prove your Liouville theorem. So in this case, you have number one. Okay, so this guarantees number one. So this condition, as I said, should be understood as certain positivity of your AU, because this lambda star is not in the closure, lambda star is outside. So that means this part has enough positivity for your AU. Eigenvalue is there. So this condition guarantees that whenever you have a super solution in a punctured ball, this will be extended as a super solution in the ball. So number one is true for under this condition. And actually, it is a necessary condition. So if this fails, you will have super solution in a punctured ball, which cannot be a super solution in the ball. So that singularity is not removed. So this condition is necessary and sufficient to remove isolated singularities for super solutions. And if you extend it inside, then the comparison theorem was already established before. So this one we already established before. So then this theorem is proved. So for theorem 2, we use the method of moving sphere. So for the method part, so if singularity is handled, this was known before. So the main thing is to handle the isolated singularity. So the method of moving sphere has the advantage that when we look at u and u phi, so we are not cutting through the singularity. Therefore, you need less control of u near the singularity to complete your arguments. For example, we only need information at the C0 level. So that's already allow us to obtain the theorems. So if you take a plane to reflect, you are cutting through the singularity, so you would need stronger estimates to handle things. Yeah. And for such equations, those type of stronger estimates are not available. So, so here we take x, we take a ball of radius lambda, finite radius. So this is the map which invert with respect to this sphere. So the first step is for every x, this is for every lambda bigger than 0 and less than lambda 0x. So for small radius, the reflection is greater or equal than u inside. This is the first step. For this step, you only need the following. So you need u is local ellipsis and positive, which we have. And you also need infinity lim inf should be positive. So this is the importance for our condition. So this is guaranteed by this AU with appropriate positivity. So AU is in gamma. This lambda star should not be in gamma bar. Namely, your gamma cannot be opening too much from the positive cone. So under this, any function with this property, positivity, you have that. Yeah. So also this is necessary insufficient. This is actually necessary insufficient. Namely, if this lambda star belongs to gamma bar, there will be smooth function so that this belongs here, but the infinity lim inf is not satisfying this. So in that case, there's no hope to do moving. Yeah, it's just in that case, the result cannot be what you want to prove cannot hold actually. You cannot prove. The proof will not work because there are yeah. Okay. So this step is to achieve that, you need to have strong understanding of u near 0. For example, well, this is one understanding, but still at the C0 level. Yeah, we are not asking derivative information in some sense. Okay. By step 1, this is well defined. So this property is true for small lambda. You go to the largest lambda, you call it lambda bar. So you know it's positive. So, but of course, at this stage, it can be positive and it might be infinity though at this moment. So step 2 is you need to prove that if lambda bar is finite, then u is identically equal to that. So once this step is established by a known result before, this problem is solved. Yeah. So this again, you need some property handling. Okay, so why this is true? So by the definition, you know that the reflection will be greater or equal than that. You know that. So you have an x, you have a ball of lambda bar x. So you know you have an order. So if it's not identically equal, then because of the strong maximum principle, we know you have strict inequality in the punctured ball. Because whenever you have equality in any of the point here, it's an interior point, then the strong maximum principle holds. So our solution is C2. So therefore, U must be equal to U phi. So therefore, you have strict positive. So now we want to show what we want. We want this limit inf of U phi x lambda bar x y minus uy. As y goes to x, you want it positive. You know this is positive everywhere. You know this is positive in the punctured ball. But at 0, they may touch. Yeah, you don't want that. You don't want it. Once you can prove that, you will see by standard arguments known before that lambda bar should be larger. So this violates definitely. You can still move the sphere further. So here, so first you know that, so we know that we have this equation is actually it's an equality solution inside. Actually, we even know it's an equality. Yeah. So therefore it's a super solution. So we want to know that it's a super solution in the ball. We want to know the U phi is actually a super solution in the ball. Namely, you can remove the isolated singularity at the center. And this is guaranteed by the fact that it is in gamma, and gamma have this property. Namely, this gamma have enough positivity. Matrices in this gamma have enough positivity. So this is true. So this is a crucial point in the proof. So you remove singularity, isolated singularity for super solution. And also this is also necessary and sufficient. This condition is also necessary and sufficient. So meaning that if this condition is violated, lambda star belongs to gamma bar, then you can always find a super solution in punctured ball, but it's not a super solution in the ball. So now we after this we know that you have a solution in the ball, you have a super solution. You have a super solution in the ball, and they agree on the a super solution on the ball, and positive here. So they cannot touch because we proved that strong maximum principle and Hopf lemma holds if one is C2 and the other is a weak solution. For example, super solution, any lower semi-continuous super solution and a C2 subsolution, they will have strong maximum principle holds, which is in this case. So our extended function is a lower semi-continuous super solution in the ball. So if you have one weak, one regular, then strong maximum principle and Hopf lemma hold. And this statement It's a general statement. Doesn't need conformally invariant. So this is a general fact. So then we prove this theorem. So I think I will stop today, and I will continue next time. And in the next time, I think I will try to present a few arguments with details. Yeah, I will pick up a few points and try to present them. For example, some of the arguments in the proof I described, I will single out some to present.
Okay, thank you.